Welcome to the first lecture for section B of MTH 204A. Since after the recent split, section B consists of MSc students only, so it is going to be an advanced level course. It is not so unreasonable to be that ambitious because they have already been exposed to some group theory in their BSc. However, to begin with, we review some topics in group theory which are taught in any standard BSc curriculum, but the students usually face difficulties. It is assumed that the students registered for this course know the definitions and examples of group, subgroup, homomorphism, etc. In this lecture, I will review normal subgroup and isomorphism theorems. So, we first recall the following two phenomena. I am sure that almost all of you have observed this phenomena earlier. So the first one goes as follows. Suppose we are given two sets and a map f from x to y. We want to make this map f bijective in a canonical way. So we define a relation on x as follows, that is x and y, they will be we define that they are related if they are being mapped to the same element of y by f. So clearly this relation is an equivalence relation on x. For each small x in capital X, we denote the equivalence class of small x by x bar, and capital X bar stands for the set of all equivalence classes under this equivalence relation. Next, we define f bar from x bar to y as follows. That is, we take a coset from x bar, so it looks like this, right? And then we map x bar to the image of x under f. So the well-definedness of f bar is immediate in view of how the relation is defined, and it's also easy to see that f bar is injective and the range of f bar is same as that of f. Thus, we obtain that f bar is a bijective mapping from x bar to range of f. Furthermore, one has the following commutative diagram in this situation. So, from x to x bar, we have the quotient map that sends every element small x in capital X to its equivalence class. And then from x bar to y, we have this map f bar defined like this. And then the definition immediately shows that the composition of this and this is this. Okay. Now the second thing that we will recall is called as the transport of structure. So here we have a set X and a group G. Assume that we have a bijective mapping from the set X to the group G. Now using this bijective map, we will make this set X a group in the following manner. So for any two elements small x and small y in capital X, so we first send them to G by f. Now once they are inside G, we can consider their product because G is a group. So once the product is taken inside G, now using f inverse, we come back to X. So that's how for any two element x and y, x star y is defined. Now it is a routine matter to check that with respect to the star, the set X becomes a group, and furthermore the map F becomes an isomorphism from the newly defined group X comma star and G. So these two phenomena that we have observed earlier, we are going to apply them in the context of a homomorphism phi from a group G to a group G prime. Okay, so first we will apply the first observation. So so that yields us a map phi bar from G bar to the image of phi. Note that here the phi bar is obtained just treating phi as a map between two sets G and G prime. We haven't used the structure preserving property of phi or G and G prime are groups, those things yet. So we just got phi bar by treating phi as a map by treating phi purely as a map between two sets. Now, using the second observation, we can make this G bar a group with respect to the following binary operation. So, for any two elements A and B, so the the A bar star B bar, what we do is we first take their images. So these are going to be phi A, phi B. So the images under phi bar, these are phi A and phi B respectively. And so this is inside the group phi G, and then using phi bar inverse we come back. So thus we can make this G bar a group, and this phi bar it becomes an isomorphism between this group G bar, which has been made made here, and phi G. Okay. So again, let me remind you that phi bar is obtained by treating phi in a purely set theoretic manner. We haven't used ever that phi is a structure, phi is a homomorphism, or even G, or even G or G prime, they have group structures. Okay, so we are going to use the structure preserving property of phi now. In order to find a nice representative of this equivalence class, that is going to be our first step towards the simplification of this artificially defined binary operation on G star. So what we do is we observe that this phi A and phi B, so this is nothing but phi of AB, right? Because phi is structure preserving. Remember that while dealing with the generality here, we cannot write fxy because we cannot write fxy because to begin with x, there is no notion of multiplication inside x. So this phi A, phi B, that immediately this is nothing but phi AB, and according to the definition of phi AB, phi bar, so phi AB is nothing but phi bar of AB bar. So now this immediately seen to be AB bar. So using the structure preserving property and of course that G and G bar has group structures, we in this situation we can see the A bar star B bar is nothing but AB bar. Okay, now we are going to use the group structure of G more to simplify it further. So well, before that, let's observe that what we have just obtained, that immediately shows the pi is a homomorphism. So let me remind you how pi is defined. Pi, in this case, pi is defined at pi of x is x bar. So for every x, so therefore this nothing but shows that pi is a homomorphism. Okay, now let me use the group structures of group structure in G further to simplify this operation. So observe that for any A in G, observe that for any A in G, if x belongs to A bar, that means phi A, according to the definition, phi x and phi A will be same. Now using structure preserving property and the relevant things, what we get is phi of A inverse x's identity. So don't confuse 1 with number 1. So it's customary to when the operation of a arbitrary group is written in a multiplicative fashion, so in that situation it's customary to denote the identity element of the group by 1. Okay, So yeah, so that's what we have observed, this that x is related to a if and only if phi of a, if and only if a inverse x is mapped to identity by phi. So we consider the collection of all such elements. So this collection is immediately seen to be a subgroup of G. We call this subgroup the kernel of phi and denote this by car phi. So therefore, star shows that x is related to A if and only if A inverse x is in the kernel of phi. Okay. Now A inverse x is in the kernel of phi. That means x lies in the in this coset of car phi, and in the coset of car phi, and therefore from this we see that since this is if and only if, so A bar is nothing but the this entire coset, okay, and consequently G bar nothing but it is nothing but the collection of all left cosets of car phi in G. I repeat, so here we have seen that x is related to A if and only if A minus if and only if A inverse x lies in this subgroup which is called as the kernel of phi. So A inverse x is in kernel of phi, it means x is in this coset. This if and only if nature of the statement immediately yields that the equivalence class of A is nothing but this entire coset, and consequently we see that G bar is nothing but the set of all left cosets of car phi in G. And in view of this, the group operation star on this G, on this collection of all left cosets of kernel phi can now be rewritten as follows. That is in this newly defined group, the product of these two cosets, that is A car phi and B car phi, is going to be the coset, or is going to be this coset. So we will just take the product of A and B and consider the corresponding coset. Okay, all right. And this map phi bar, which sends a coset a times car phi to phi a, is an isomorphism between this group to phi G, and we have the following diagram. So from G to this collection of left cosets, we have this quotient map pi, which we have already observed an homomorphism, and the phi bar from this group to this group becomes an isomorphism. So thus, as a corollary, we find that this group G mod car phi is isomorphic to phi of G. So whenever a homomorphism phi is given from G to G prime, we can make this the set of all left cosets of car phi in G a group in this manner, and that group becomes isomorphic to the image of phi. So this is what we usually call as the first isomorphism theorem. So note that we have never used any notion called normal subgroups here. We just took a homomorphism, then we apply our previous observation, which leads us to the equivalent to this equivalent set of all equivalence classes. Then using the structure preserving property of phi, we see that in this context the multiplication takes this simpler form. Now exploiting the group structure of G more, we see that the elements in G bar, namely the equivalence classes, are nothing but the cosets of kernel of phi. So therefore now the collection of cosets is collection of cosets that becomes a group with respect to this operation, and that group is isomorphic to the image of phi. So we have never used any notion, any concept like normal subgroups or factor groups. Okay, but now we are going to introduce that concept. So let me put a remark here. In the usual textbook, the approach is usually the opposite one. That first normal subgroup is defined, then quotient, then factor group comes, and then finally we arrive at First isomorphism theorem. But here, as I said, here this approach is an opposite one, that we first directly prove the first isomorphism theorem from two elementary observations. Namely, the first one is how to make a map bijective, and then secondly, the transport of structure. We directly make this G directly make the set of all left cosets a group in a very natural way, as I said, and in that process it automatically comes that the way the group structure is made, it automatically becomes isomorphic to image of phi. Okay, so as I said that I'm now going to introduce normal subgroups and everything. So let's first observe that in the law, in the what we have just observed. Let's first observe that what we have just discussed. There, if H is if a subgroup H is the kernel of some, if a given subgroup H of G is the kernel of some homomorphism from G to some other group, then the set of all left cosets, which is denoted by this symbol, it forms a group. With respect to star, which is defined like this. This is what we have just observed. So it's a very natural question that for which subgroups we are going to have the similar phenomena. Let me repeat. We have earlier we have observed that when if the given subgroup H is the kernel of some homomorphism, then G mod H forms a group with respect to the operation defined like this. Now it is very natural to ask that for which class of subgroups of G, this phenomenon holds, that is the set of all left cosets can be made a group with respect to a binary operation defined like this. Okay, so the question that we are going to ask is we will put the question in the generality. So if G is a group and H is a subgroup, so does the following always define a binary operation on the set of all left cosets? So does this always define a binary operation? And for the next thing is, if this forms a binary operation, then with respect to the binary operation, does the set of all left cosets of H in G become a group? Okay. While answering to this question, let's first observe that the second question has an affirmative answer if the first question has an affirmative answer. Okay. So that's quite easy to see, because if this indeed this gives us a binary operation on this collection, then from the associativity and from the group properties of G, from the group properties of G, all the required properties for this star to make this group immediately follow. So the crucial part is, so therefore the main point is this question, because once this is settled, then the rest just becomes an immediate corollary. Okay, Now let's see that whether this always defines a binary operation on this collection or not. So what we do is we'll let A be xy in G such that AH equal to XH and BH equal to YH. Now this ABH equal to XYH holds if and only if Y inverse X inverse AB lies in H. Now since H equal to XH by your assumption, so X inverse A is already in H. So here this is already in H. Okay. So this is already in, so if, let's denote that by small h. Therefore, this holds if and only if Y inverse HB is in H, and that should hold for all ABX, and Y. Okay. But you see, like this is in H, but this is perhaps not in H. This is perhaps not in H. So, in general, there is no reason to expect that for whatsoever A, B, X, Y you choose, this quantity always lie inside H. So, in general, the star given is the star given by this cannot be expected to be well defined, and consequently one cannot expect that that will make the collection of left cosets a group. Okay. So we see that the answer. So we see that in generality we cannot expect that the answer to the first question is going to be affirmative. So what we will be doing now is we will try to find a sufficient condition so that we're going to sufficient condition leading us to a class of subgroups for which this becomes well defined, and consequently we can make this into a group. Okay. So how to find a sufficient how to find a natural sufficient condition. So let's go somewhat slow and observe something very simple. That is, if suppose the group is abelian, then we can simply switch this and H and Y inverse. So since by equal to H, BH equal to YH, so by inverse B will be in H, hence then the product will be inside H. So if G is abelian, then certainly this is going to be a binary operation for any H, and hence this is going to be a group. Okay, so abelianness can be a sufficient condition. Let's try to find something even more general. So you see that in order to run the argument which I have just given, you actually don't need any two elements in G have to commute. That it's enough that if any element of G commutes with any element of H, even that would be enough. Even then we can simply switch them and we will get the product inside H. So therefore this might this might lead us to a further general collection, and even a much more careful thought will reveal that we even don't have to have that every element Y, every element of G commutes with every element of H. Rather, what is enough for our purpose is if Y inverse H is some H in H prime Y inverse. Because what all we need is we want to bring Y prime on the here, and in that process if H is being changed to some other element, that's not a problem as long as that changed element also lies in H. So therefore even this is enough for some H. So in view of this observation, we see that the sufficient condition, what we are seeking should be the following. That is, for every A in A, G, and H in H, AH should be some H prime A for some H prime in H. If that is there, then certainly, if this is there, then immediately we will have all such things will be inside H, and that makes star a binary operation. Consequently, the left collection of left cosets becomes a group with respect to star. Okay. So this condition is can be equivalently expressed in terms of cosets like this. So for every A in A, the left coset of A in the left coset of H by A is same as the right coset of H by A. So therefore, so this condition, that is, for every, so each left coset is same as the corresponding right coset. One cannot expect that to hold for any arbitrary subgroup of G. So since it cannot hold it we cannot expect that it holds for any subgroup. So we will focus our attention on that class of subgroups for which this happens. Because that for any H satisfying this, we get that the star defined here, here becomes a binary operation, and consequently this becomes a group. Okay. So therefore the collection of therefore the subgroups H for which this property which this property holds, the subgroups H for which this property holds, actually deserve a special place in the theory. So that leads us to the definition of normal subgroups. So a subgroup H is said to be normal in G if it satisfies one of the following three equivalent conditions. The first condition is just what we have seen here. The second condition is nothing but the conjugate of H by A, which is defined to be this collection. This is exactly H. And the third one seems to be a slightly relaxed one. That is, here we don't require that the conjugate is to be H. Rather, what we demand is for any A, the conjugate will be contained inside H. So the equivalence of these three, because as I said that if it satisfies the following equivalent conditions, so I am leaving the proof of equivalence of these three things as an exercise. So if H satisfies one of them and equivalently all of them, then we say we call H a normal subgroup of G, and we use this notation for that. What are the examples? For any group G, trivial subgroup and G are always normal subgroups of G. If G is an abelian group, then certainly any subgroup is normal. If F is, let's say, the field of rationals, reals, or complex numbers, then matrices with determinant 1 is a normal subgroup of the matrices of the collection group of all invertible matrices. So here the group, let me remind you that this forms a group with respect to matrix multiplication. The fourth example is for any group G, we define the collection of all group elements which commute with every element of G. So this is called the center of G, and it's obvious that the center of G is a normal subgroup of G. Okay. If a subgroup has index 2, then it's normal. That's a trivial verification. And the next we talk about if two normal subgroups are given, from that how to make another normal subgroups of G. So if we take their intersection, that also becomes a normal subgroup of G, and their product, namely it consists of the elements of this type. So it's easy to see that this forms a subgroup. This forms a subgroup of G, and in fact the subgroup is normal. Okay, so before we go ahead, let me say a few remarks. So the first remark is that normality is a relative notion, it's not an absolute notion. What I want to mean by this is, like if H is a normal subgroup of G and G is a subgroup of some bigger group N, then H may not be a normal subgroup of N. This can be easily seen. So what you do is, if H is a subgroup of N, which is not normal, which is not a normal subgroup of N, then once we take a G equal to H, we see that H is normal in G. G is a subgroup of N, but H is not a normal subgroup of N. So whenever we want to talk about a normal subgroup, it's absolutely necessary to mention that where the given subgroup is normal in. And of course, when there is no bigger group containing G, in that context, one can omit the reference of G if no confusion arises, but not otherwise. Okay. So for simplicity, of course, we can omit the reference of G, but we have to make sure that it doesn't lead to any confusion. So therefore, whenever we will be very careful while talking about normal subgroups. So every time we will strictly mention it's the given subgroup is normal in which group, or normal. No, yeah. The second thing we want to remark is the normality is not a transitive relation. That is, if H is normal in G and G is normal in N, then H may not be normal in N. So of course there are easy examples for both these remarks. So I am leaving the task of finding appropriate examples. I am leaving the task to you as an exercise. Okay. So now let's observe that the condition normality, we have obtained the condition called normality as a sufficient condition for making the set of all left cosets a group with respect to the star which has been defined earlier. Okay. Previously we saw that when the subgroup was the kernel of some homomorphism, then the star becomes a binary operation, and then we get the left cosets that forms a group. So, like, try to understand. In the beginning of this lecture, we found that being the kernel of some homomorphism is a sufficient condition. Then right now we have obtained normality as a sufficient condition for being star a binary operation, and the rest. So it's a very natural question that whether there is any connection between these two things, that is being the kernel of a homomorphism and being a normal subgroup for a given whether there is any connection between these two things, that is being the kernel of an homomorphism and being normal in G. So this theorem answers that. So for any group G, the following things are equivalent, that is, it's normal in G and it's the kernel of some homomorphism from G. So for the proof, so this direction is just a routine verification. For this direction, we consider the quotient map. Remember, since H is now assumed to be normal subgroup of G, so therefore this becomes a group with respect to star. So that makes pi a homomorphism, and it's immediate that its kernel is H. So thus we have seen that the notion that we have found in the beginning of this lecture, that is being the kernel of some homomorphism, and that one which we found later, that is being normal, in being a normal subgroup of G, these two things are actually equivalent. So it's not the case that one class is containing the other properly. All right. So again, let's come back to what we are talking about, that is normality. We have found normality as a sufficient condition so that this becomes a group. Now it's a very natural question whether that is necessary. So the next theorem answers that. So if G is a group and H is a subgroup, and star defined like this, if this is a binary operation on G, then if the binary operation on the collection of left cosets, then H is normal in G. Try to understand earlier what we have proved, that if H is a normal subgroup of G, then star defined like this becomes a binary operation, and consequently we got this as a group. But now what is given to us is star is a binary operation on this collection, and then H will be a normal subgroup of G. To show that, what we will do is we take an arbitrary element A in G and H in H. From the hypothesis, we must have that EH star A inverse H will be A inverse H in one hand, and on the other hand, EH can be written as HH, and therefore that leads us to H A inverse H. So since this coset is equals to this coset, we must have AH A inverse in H. And so in view of the third condition of among these three equivalent statements, we see that H is normal in G. So therefore, thus we have found that the condition. So again, let me remind you, our objective was to make the set of our left cosets of H. Our primary objective was to make that a group with respect to star, and of course, in general, we cannot expect that to happen, as we have already seen. So therefore, we will be looking for some natural sufficient conditions, so that we get a larger class of subgroups for which we can get the left cosets a group by star. And in that process, we found normality is a correct sufficient condition. Now this theorem answers that's necessary too. So therefore, that shows that we cannot have anything better. All right. Next, we define the multiplication of two subsets of arbitrary subsets of G. So that's defined in a very natural way. So remember that it's defined exactly in the way of the product of two subgroups. So now S and T are arbitrary subsets. So So now for a normal subgroup H of G, we can consider the multiplication of two cosets of H in two ways. One way is, of course, by star, which we have defined earlier, and another way is we treat the cosets as two subsets of G and multiply them by this very natural multiplication. So we have two ways to multiply two cosets. So it's quite natural to ask whether there is any relation between these two multiplications. We now answer that. So we prove the following proposition, which says that if G is a group and H is a subgroup, then for all A, B in H, the coset of AB is contained in the product of these two cosets. So remember here it means, so remember here here this product is in this sense. Okay, so that's in fact quite easy to see. And the interesting part is regarding the equality. So if H is a normal subgroup of G, then there will be equality, and in that case, in one hand ABH will be H times BH, and on the other hand, due to normality, ABH is going to be AH star BH. So when H is a normal subgroup, we see not only the equality happens here, also these two multiplications with what we are talking about, they actually coincide. So as usual, this is a routine verification, so I leave the proof to you as an exercise. Yeah. So thus we have, so in view of this proposition, what we have obtained is the following, that on this collection of cosets, the multiplication star, which is defined in somewhat an abstract way, namely, or abstract or artificial way. So in this situation, that actually coincides with the most natural thing which can can be considered, namely the multiplication of the cosets. Okay, I repeat that in the situation when we are having H normal, then the binary operation of this group becomes the usual multiplication of cosets. The usual means here is this one. Again, let me remind you. So now in this situation, star becomes just the usual natural multiplication of cosets, nothing artificial. Now assume that let me tell you what we are going to do is so here we have observed that if H is normal, then the binary operation of this group becomes the natural multiplication of cosets. Now we are going to answer its converse. So suppose we are given a group and a subgroup, given a group G and a subgroup H, and it's also given that for any A and B, the usual multiplication of these two cosets is equal to this coset. Then suppose this is given to us, then we see that the star defined like this becomes well defined. Why? Because if H equals to A prime H and B equals to B prime H, then you look at AH star BH. This is the way star is defined. In one hand it will be ABH, and since we have this in this situation, then AHBH. Now AH can be AHBH. Okay, so again that's AHBH, and again AH star BH star. So if it is given that is for a equality holds here, then star becomes well defined, and we have already seen if star becomes well defined, then H has to be normal. Therefore what we have obtained is that this condition for every A and B, AH BH, the usual multiplication of these two cosets becomes, this cosets is equivalent to have H is normal in G. Try to understand. First, here we have proved that if H is normal in G, then we have equality here, and consequently so if we have if H is normal, then we have equality here. And now we have answered the converse one, that is, if we everywhere we have equality, then H also becomes normal, because in that case star becomes well defined. All right. So we get yeah. So as I said that yeah. Okay, so let's go ahead. So suppose that we are given the left cosets of H in G forms a group under natural multiplication of cosets. So then one must have H ABH equal to ABHY, because remember that it's given that it forms a suppose remember that it's given that this collection set of all left cosets forms a group under natural multiplications, and then therefore for any A and B the natural product of these two cosets will be a coset, and already you have observed in the generality that it contains this coset, so it has to be a coset and contains another coset, so there is no other option, it has to be this. And once this is this, we have just observed that H has to be normal. So what have we got here? So try to understand here. We have proved that if H is normal, then G mod H becomes a group with respect to natural multiplication of cosets. This is what we have observed here. Now suppose it is given that so if H is normal in G, then the set of all left cosets becomes a group with respect to natural coset multiplications. And conversely, suppose if it is given that the set of all left cosets forms a group with respect to natural multiplication of cosets, then we get H has to be normal in G. So that gives us another way of looking at normality, that is H is normal in G if and only if the set of all if and only if all left cosets of H in G form a group under the natural multiplication of cosets. So again, let me remind you, first we have proved that if H is normal, then with respect to natural multiplication of cosets, this becomes a group. And here we have seen that if it is given that with respect to natural multiplication of cosets this is a group, then from that we get H is normal in G. So putting this two together, we see that the left cosets will form a multiplication which will form a group with respect to this natural multiplication when and only when H is normal. So whatever we have discussed so far, we have seen several equivalent characterizations of normality, right? We have discussed one after another, so we summarize everything into the following main theorem. So it says that the following are equivalent, that is H is normal if and only if so the equivalence of first three is already mentioned in the definition of normality. Now later on we further got two things, that is for every natural product of AH and BH as subsets of G becomes ABH. And the fifth one, that all left cosets of H, it forms a group under natural multiplication. So we have found all these are equivalent. All right. Okay. So now it's now the time to make give a name to this collection of set of all left cosets of H in G. So if H is normal, when H is normal in G, we have thus just discussed that when H is normal in G, then this collection becomes a group with respect to natural multiplication of cosets. So this group, again the set is the set of all left cosets, and the operation is now the natural multiplication. So this group is called the quotient group of G modulo H, or factor group of G modulo H, and it's usually read as G mod H. And if A and B are in the same coset of H, that is AH equal to BH, then we often say is congruent to B modulo H, and write this, and write that by this. Well, you might be quite curious why we are using this word modulo. This is exactly because, this precisely because of the following, that for any natural number n, if you remember, Zn is nothing but the set of all equivalence classes, right? Set of all equivalence, Zn is this, okay? Now, if you just observe more carefully, for any k bar is nothing but the numbers which so k bar is nothing but the numbers which leaves remainder k when divided by n. So therefore it is nothing but k bar is nothing but this coset. So thus this Zn that we have seen earlier is nothing but this quotient group. And like inside Zn, whenever A bar equal to B bar, that happens if and only if A is congruent to B modulo n. So since Zn is a special case of factor groups. So we carry out the terminology for Zn, we carry out the terminology which we have earlier used for Zn we carry over that terminology to other general factor groups as well. Okay, so I think I have made my points. I have made my point clear that Zn. So this modulo, this term modulo is associated with Zn, and Zn is observed to be exactly this quotient group. So therefore, now we carry over the terminology which we usually use for Zn to any general factor group, Yeah. All right. So thus we have discussed normal subgroups and its equivalent ways of looking at that. So let me again remind you that we first proved this first isomorphism theorem directly without the notion of normal subgroups. Then while proving the isomorphism theorem, we saw that for kernel of homomorphisms, we can make this left cosets as groups with respect to star. Now we ask that question in the in the context of now we ask that question in the context of any subgroup, and then we try to see what sufficient condition can help us out, and that leads us to normality. So as I keep saying that here our approach is the opposite one. So first we proved the isomorphism theorem directly, then we introduce normality, then factor groups. Okay. So in the rest of this lecture, I will be proving second and third isomorphism theorems. So as I said that maybe all of you have already seen those theorems, but the only difference in this lecture is we will be establishing those theorems in a different language. So namely using the language of exact sequences. You may ask that why it's necessary to use that language when those theorems can be established in the usual manner, in the usual language. So the reason is that like I completely agree that this can be used these theorems can be established in the usual in the usual language. However, the language of exact sequences will be extremely useful in algebra later on. So it is so it is not a bad idea, or perhaps it is a good idea to put the known things to put the known things in this new language, and that will in fact help that will indeed help us to understand the language better. All right. So suppose we are given two homomorphisms. So we are given groups G, G prime and G double prime, and we are given two homomorphisms F from G to G prime and from G prime to G double prime. It is customary to put them in the following way, and we call it a sequence of homomorphisms. And and such a sequence we call it exact if the image of F is kernel of G. Let me give you an example. So suppose H is a normal subgroup of G. Then we consider this sequence from H to G. We have the inclusion that it sends every small h to H itself. But here H is viewed inside capital G. And then from G to G mod H we have the quotient map. And the kernel of the quotient map is H, which is exactly the image of I. So this is an example of an exact sequence. So more generally, so here you see this sequence has one joint, namely here. So more generally, we can talk about sequences of homomorphisms having multiple joints. That is sequences of this type. So here we have let's say n groups and n minus 1 homomorphisms like this. So F1 is so Fi is a homomorphism from Gi to Gi plus 1. So for such a sequence, by exactness I will mean that it's exact at every joint. That is for every I imaginary part for every I image of Fi is kernel of Fi plus 1. So yeah. So now we let 1 stand for the trivial group with exactly one element. So it is customary to denote the trivial group by this here. So don't be confused that as I said that this 1 is not the number 1, the usual one. So earlier, in this lecture we said that the identity element of a group, when it is written multiplicatively, you denote the identity element by 1. And when the group is trivial, then we simply remove the curly brackets and write this by 1. So from the context, we have to understand that whether 1 denotes the trivial group or the identity element. So yeah. So given this trivial group, it's easy to see that there are unique homomorphisms in each of these cases. Okay, so here this is just the map which sends the only element in this trivial group to the identity element of G, and here it is basically the trivial map. So sending all elements to the only element in this trivial group. So the following are obvious from the definition that a sequence like this is exact if and only if F is injective, because the image, because here image is nothing but the nothing but the trivial subgroup of G, and this exact means kernel is trivial, therefore F has to be injective. Similarly, this is exact if and only if G is surjective. This is exact if and only if both injective and F is both injective and surjective, that is F is an isomorphism. And a sequence of this type is exact if and only if this F is injective, the G is surjective, and image of F is kernel of G. An exact sequence of this type is called a short exact sequence. Let me give you an example of a short exact sequence. So, given a G and a normal subgroup H, the following is a short exact sequence. That is, here we have the inclusion map, so which is obviously injective, and then we have the quotient map which is objectively surjective. So therefore this becomes a short exact sequence. So this is an example. So this is for any G and H. This gives us an example of short exact sequence. Now what we are going to see is, in fact, that every short exact sequence must be of this form. So what I mean by this is the following. That is, given a short exact sequence, there exists a normal subgroup H such that this short exact sequence is same as this short exact sequence. So here, by saying same, I mean that there are isomorphisms from G prime to H and G double prime to G mod H, such that the following diagram is commutative. So diagram is commutative means each square commutes. Okay, so so given any short exact sequence, there exists a normal subgroup there is a normal subgroup and two isomorphisms such that this diagram commutes. So this is what I mean by saying that any short exact sequence is of this form. So the proof I have left as an exercise. I can give you just a hint that what you can take is, so the f of G prime is going to be a subgroup of G, right? And from the exactness, this is exactly kernel of G. So this is actually normal in G. So you can take H to be this. Okay. So I leave the rest to you as a routine exercise. So what does this observation tell us? As I said, that any short exact sequence is indeed any short exact sequence is same as a short exact sequence of this form. So what does that tell us? That tells us that given a short exact sequence, we can regard G prime as a normal subgroup of G and G double prime as the quotient group of G modulo G prime. So we see that a short exact sequence is nothing but an alternative way of displaying a normal subgroup of the given group and the corresponding factor group modulo that normal subgroup together with the natural maps. So therefore, now you see that short exact sequence is nothing but an alternative way of displaying a normal subgroup and the corresponding factor group of the given group together with the natural maps. Okay. So try to understand that. First, we saw that every short exact, so this for any group G and normal subgroup H, this is a short exact sequence. Then we have proved that every short exact sequence is same as a short exact sequence of this form. So thus this says that these are the only types of short exact sequences. Therefore, loosely speaking, we can regard a short exact sequence as nothing but another way of displaying a normal subgroup and the corresponding factor group of a given group together with the natural maps. All right, let me make a remark here. So earlier we considered exact sequences having multiple joints, but we have considered only finite sequences. Now we can even generalize that. We can now consider infinite sequence of homomorphisms. Namely, so for simplicity, we will only we only consider that our collection is indexed by Z. So we have therefore for each I we have a homomorphism Fi from Gi to Gi plus 1, and so this so this sequence of homomorphisms is said to be long exact if for each I kernel of Fi plus 1 is image of Fi. So long means we indeed have infinitely many groups, infinitely many homomorphisms indexed by Z, and if at every so thus we have infinitely many joints. If it is exact at every joint, then we call it a long exact sequence. The crucial observation here is any long exact sequence can be reduced to a collection of short exact sequences, and that collection is indexed by Z in the following way. That is, for any I, what we do is we consider Ki to be the kernel of Fi, and kernel of Fi is therefore for each I we have this. That is, in one hand I consider kernel, one hand I consider Ki, and on the other hand I consider Ki plus 1, which is nothing but image of Fi. So thus given a long exact sequence, for every I in Z we have a short exact sequence just by considering the kernels of Fi's. Okay. Now we will be proceeding towards the proof of second and third isomorphism theorem. The following is just an useful extension of the first isomorphism theorem. It says that given a group homomorphism, suppose that n is a normal subgroup of G contained in kernel of phi, then there exists a unique homomorphism F bar from G mod n to G prime. We have a homomorphism such that the diagram is commutative. All right. So just to understand what is going on, I would advise you to consider the situation when n is the whole kernel of F. In that case, F bar is the map which sends F bar is the unique map that makes this diagram commutative. And how was that map defined? It sends the kernel, a coset of the kernel, to the corresponding image of any representative of that cosets under the homomorphism F. Okay. So this is, as I said, an extension of first isomorphism theorem, because here we don't expect that, we are not insisting that n will be the whole of, we are not expecting that n will be whole of kernel F. Rather, we just expect it's a normal subgroup which is contained inside the kernel. All right. So, and F bar is injective if and only if n is equals to whole kernel. So, as I said that here F bar is defined exactly in the similar manner that we have done in first isomorphism theorem. Any coset is being sent to this. The well-definedness part is taken care by this inclusion, and the rest, that is the commutativity diagram is obvious, and that this injective if and only if n is kernel of F, that is left as an exercise. So this is, as again I am saying that this you may regard as a very natural, or as a natural extension of the first isomorphism theorem. So here n does not require to be the whole kernel. As long as it is a normal subgroup contained inside the kernel, we can adopt the same strategy that gives us a map F bar here, heavy with making this diagram commutative. Now this map may not be injective always. It will be injective if and only if we are at this situation of first isomorphism theorem. Okay. We will now deduce a corollary of this which will be used later on. So given by a normal pair, I mean a group G and a subgroup A and a normal subgroup H of G. So when two normal pairs are given, so a homomorphism between two normal pair by a homomorphism F between this normal pair and that normal pair, I mean it's a homomorphism from the group G to G prime such that it carries H inside H prime. So by a homomorphism between two normal pairs, I mean it's a group homomorphism that carries this normal subgroup inside that. Okay. So now as a corollary of this extension, we see the following, that is for any homomorphism between two normal from the normal pair G comma H to G prime comma H prime, there is a unique homomorphism from the corresponding quotient group to this quotient group such that the following diagram commutes. I repeat, so we are given a homomorphism between two normal pairs. So whenever it is there, so whenever a homomorphism between two normal pairs F is given, we're using this extension, we get a unique homomorphism F tilde such that this diagram commutes. So here each row of this diagram is a short exact sequence, and this FH is nothing but the restriction of H to H. That makes sense because F is a homomorphism from the normal pair G comma H to G prime comma H prime. And furthermore, this F tilde is injective if and only if H equals to F inverse H prime. And in this case, F tilde becomes an isomorphism if F is onto. So this is, as I say, a routine as an easy corollary of this. So I leave it to you as an exercise. Okay. Now, now it is the time to prove the two isomorphism theorems. We'll first prove the third one. So it says that if H and K are two normal subgroups of G, where H is also a subgroup of H, both are normal subgroups of G, and H is also a subgroup of K. Then there exist homomorphisms which make the following diagram commutative with each row exact. So, what do we have? We have two normal subgroups H and K of G, and H is further a subgroup of K. So in that situation, so for both H and G, we have the corresponding short exact sequences, and then there exist we have two subgroups, normal subgroups H and K of G, and H is also further subgroup of K. Then for H we have this short exact sequence. Now the third isomorphism theorem says that there exist homomorphisms such that this diagram commutes, where of course I is the inclusion, pi H is the quotient map. I use the letter H because I in this context we have two quotients. One is modulo H, another one is modulo K. So I didn't distinguish their corresponding quotient maps by by putting h and k in the suffixes. This map is the quotient map, and we restrict that to h, and this map is identity. So according to the third isomorphism theorem, we have homomorphisms such that this diagram commutes. Okay, and such commutes, and each row is exact. So since each row is exact, therefore as it follows immediately that this is nothing but the quotient of g modulo k modulo h modulo k. So that follows from the exactness. So how to prove such a theorem? So we have to find the appropriate maps, right, in the bottom row. So so what we do is let's first try to find this map. So from h to g we have inclusion map, and then once we compose pi k with that, we have a map from h to g mod k. Okay, we have a match from h to g mod k, and observe that I think just a small mistake. Rather, k will be contained inside h. Sorry. Yeah. So therefore, therefore it's easy to see that the subgroup k, this normal subgroup k of h, is contained in the kernel of this map, which is obtained by this composition. Therefore, from the extension which we have talked a few minutes back, using that gives a map. So this is pi k compose I. So this is the map pi k compose tilde. So it's easy to see that it just sends a coset here, this coset bk to this coset hk here, any coset hk to itself, but here it is viewed as a member in g mod k. And for this we will again use this do the similar things that we we consider pi h, which is a map from g to g modulo h, and of course k is contained in the kernel of that. Therefore there is a map which makes this triangle commutative. So in our notation, this is pi h tilde. So so from the construction, commutativity is already there, and the verification of the exactness of the last row is left as an exercise. Remember that you just have to keep in mind that this map sends hk to the same hk inside g mod k, and here a coset gk to the corresponding coset of h. Okay, so in view of this too, the exactness is almost immediate. Okay, so we'll finish this lecture by proving the second isomorphism theorem. So here we have two normal subgroups h and k. There nothing is assumed whether h is contained inside k or not, or k is contained inside h. So these are just two normal subgroups of g. Then one has the following, that is, the intersection is a normal subgroup of h. Of course that has to be true because intersection is a normal subgroup of g, so it has to be normal in h. Then hk, once h both are normal, then hk will be equal to kh, and that will be of course a subgroup of g. In fact it will be normal. But in this theorem we don't actually need that. The important part is when these are normal, then this is indeed going to be a subgroup. So once this is a subgroup, so this subgroup we can easily see that this subgroup contains both h and k. Since k is normal in g, k is also normal in this subgroup hk. Hence it makes sense to talk about hk modulo k. On the other hand, we have h modulo h intersection k. So the second isomorphism theorem says that these two factor groups are isomorphic. So the proof, so for the proof, this one is trivial. This is again a routine verification. Hence, you have to work out the details. And to prove the third one, observe that from H to HK modulo K, we have this homomorphism. So this is nothing but, so each small h maps to HK, and we look at the kernel of this homomorphism. So it's a easy verification that the kernel is nothing but a intersection K. Now this conclusion is immediate in view of the first isomorphism theorem. So this second isomorphism theorem is basically an immediate corollary of the first isomorphism theorem. But for the third one, we here rather used a strengthened version of the first isomorphism theorem that not only gives us this isomorphism, also it gives us how these various groups are naturally connected, and that's displayed in this diagram. In the diagram having each row exact. All right. So I think with this I will finish this lecture. This completes this completes all the relevant things regarding normal subgroups and the isomorphism theorems in group theory. Okay, I will stop here.